Okay. Now, so I'm going to go back now to give you the screen back here. I'm going to go and go back to this page we were on a minute ago that you saw, because I want to do something else. I want to make sure we can do triangles and things in trig. So this next thing here is, suppose somebody gives you, and this is a problem in Appendix D, suppose somebody gives you this thing. Now, at the first, they're not going to give you all this. What the book gives you is what I'm covering up everything except what the book gives you. They give you the sine of theta is 3/5. Theta is between 0 and pi over 2. So first, why do we care where theta is? And the answer is that theta can be anything from 0 to billions or minus billions. In this case, it's what we call in the first quadrant. It's between 0 and 90 degrees. So if I make a two-dimensional graph with an x and y axis, we're talking about the upper right fourth of the plane. It's called the first quadrant. The trouble is that if I didn't say that, and I know this is true, then the angle might be in the third quadrant, because the sine function is positive in the third quadrant, and you're supposed to know that. So if I do a different problem here, namely if I change the angle to the third quadrant, it's going to make some of the other 5 things in the 6 trig functions with different answer. But in the first quadrant, all 6 trig functions are positive. And if you then, what I always do is draw a triangle. Now in this case, I wouldn't even worry about the whole plane and 2 dimensions and all that. I would just worry about drawing any old triangle like this. And the little box here, I think you know, means a right angle. I'm looking at just a second here. I gotta get something's covering over what I'm doing on my own screen, and so when I look at this, I don't do it very fast. Okay, that's a little symbol for right angle, right triangle. I assume you know that. And they only gave me the sine of theta is 3/5, but I know, supposedly, because I know trigonometry, that that's the opposite over the hypotenuse of the angle. The side opposite the angle is the one with the 3 on it, and the hypotenuse is the one with the 5 on it, and the sine is 3/5. And so you put the 3 on one side and the 5 on the hypotenuse, and that gives you a geometric picture of what the information they gave you. Now, I'm covering over the other side, which you get the length of it from the Pythagorean theorem. So a 25 minus 9 is 16. The square root of 16 is 4, not -4, just 4. Okay. Now, however, we're going to have some -4s come up maybe in a little bit, because some trig things we write -4, even though it's not really. It's a length 4, but its position will make it a -4. We'll deal with that in a minute. I'm assuming you know the other definitions. The cosine of an angle is the adjacent side, that's the 4 side over the hypotenuse. The tangent is the opposite over the adjacent, and so on. I'm assuming you can do this problem. You are supposed to be able to do everything in the appendix. It's one of the problems there. Now I'm going to give you another problem there. And that's this one. And I'm going to cover it over a little bit first. This wants to give me the cosine of x is -1/3, but x is between pi and 3 pi over 2. So this time you draw a 2-dimensional thing like I'm now depicting, hopefully. And the x is a number that gives you an arc length, and it's in the 3rd quadrant because pi is the minus x-axis and 3 pi over 2 is the minus y-axis. And so I have an angle in between, so I draw this triangle. Now, key here is always draw the triangle to go to the x-axis, okay? So when I make this angle involving x, I have a line. I don't take a line over to the y-axis. I always take a line to the x-axis. And this is a triangle we want to do. The cosine is the adjacent over the hypotenuse. In this case, it's negative. Anything to the left here is a negative on the axis. So I put -1 there. It's actually length 1, but we write -1 to indicate where it is as well as what it is. The hypotenuse is always 3. We don't ever put -3 here. Always positive. Hypotenuse is always positive. In this particular case, when I did a Pythagorean theorem, I get 9 minus 1, because 1 square is 1. 9 minus 1 is 8. I have to take the square root of 8. That's 2 square root 2. Only positive 2 square root 2. Okay? But in this case, its position means I put a negative on it. That's not because the square root of 8 is ever negative 2 square root 2. It's only because I'm writing the thing in the plane to help me, where I denote this as minus. Now, has anybody got a problem with that?
Wait, so okay, so I get where you got the -1 and 3, but where do you get the -2 and square root 2? Because that would be, to get the Pythagorean theorem, it'd be 9.
9 minus 1.
Yeah, it would be 8, which would be 4.
And 8 is 4 times 2.
Then you
The square root of 4 times 2 is the square root of 4 times the square root of 2, and that's 2 times square root of 2.
Okay.
If you would rather, I could write here minus the square root of 8. That's the same thing.
Yeah, I get it either way. I mean,
writing this minus square root of 2 square root of 2 is called simplifying the square root of 8.
Yeah.
Okay. And it's usually easier, not always, you don't always have to do it, but it's usually easier to write the simplest number you can for any real number. Not always. Sometimes it doesn't matter. Okay. Now, what are the 6 trig values now of the 6 functions? Well, if you know about opposite, adjacent, and hypotenuse and stuff, you do the 6 things. So I just did 2 of them over here. The sine is the opposite. That's the -2 square root of 2 over the hypotenuse. The tangent is the opposite over the adjacent. In this particular case, it becomes positive. You ought to know that in the third quadrant, only the tangent and cotangent are positive. So in this answer, if I did all 6 of them, 4 of them would be negative and 2 of them would be positive. I've written down the sine is negative. The other negative one in this case, not the other 3, the cosine would be negative. You already know that. And the reciprocals of those 2 numbers would be negative. Those are the secant and the cosecant. So 4 out of the 6 in the third quadrant, 4 out of the 6 answers are negative. In the second quadrant, 4 out of the 6 answers are negative, but different ones. In the fourth quadrant, 4 out of the 6 are negative, but different ones. Now, when I was in high school or someplace, what I learned, and some of you may have seen this, there's different ways to do this. I was made to memorize this nonsensical word. That's how I was taught, is memorize this word. And what it says is everything is positive in the first quadrant. The sine and its reciprocal are the only ones positive in the second quadrant. The tangent and its reciprocal are the only ones positive in the third quadrant. And the cosine and its reciprocal are the only ones positive in the fourth quadrant. That's what I did. Now, you guys can probably tell me other ways you remember that, because it's taught in several different ways. And any way is good as long as it works for you. But I thought we ought to talk about this a little bit. Anybody else want to say anything about that? Then I want to go to the.
I was gonna.
Please.
Okay, so I know. Okay, in high school, we weren't allowed to have square roots on the bottom half of a fraction. Is that still a rule here or not?
Yes and no. Okay, let me give you sort of a general statement about that. Okay. Suppose that I have 1 over, now I want you to just think this in your head, okay? suppose we know that the square root of 2 is like 1.414. I don't know if you know that or not, but when I was in school, we didn't have calculators, so we had to learn some of the common things like square root of 2. 1.414 is what I learned, okay? I learned it to 3 decimals. That's just what we were taught. In the back of all the books when I was in high school were tables that had these answers, had these numbers. Anyway, so square root of 2 for me is 1.414. I can't forget it. Square root of 3 is 1.732, and so on. I happen to know about 100 of them, but that's not the point. So, okay, 1 over the square root of 2 would be 1 over 1.414 when I was in high school. And that was bad because you had no idea what that was. 1 over 1.414, that was some kind of long division problem because we didn't have calculators. And so that was bad because you couldn't tell about how much it is. It's very difficult in your head to say, oh, I'll just divide 1 by 1.414. Okay, most of us can't do that. So if you multiply numerator and denominator by the square root of 2, then the denominator becomes 2 and the numerator becomes the square root of 2. And so you write, as was suggested by the question, you write 1 over the square root of 2 as the square root of 2 over 2. Now, look at square root of 2 over 2 and replace that by 1.414. If I have 1.414 over 2, in my head I can get 0.707 because 1414 divides in by 2 to 707. So in my head, without doing any computation, 1 over the square root of 2 is immediately 0.707. That's pretty good. Okay, so if I know what the square root of 2 is, I know what 1 over the square root of 2 is by doing a process called rationalizing the denominator. Okay, so why was it taught that way? Why has it always been the way they did it in high school? Because we used to have to do long division to see what decimal it was. Okay, and so mathematics was developed to enable one to quickly be able to compute, and dividing 1 by 1.414 is a heck of a lot harder than dividing 1.414 by 2. So the reason it was done was to get us answers. Okay, now when you have a calculator, the calculator doesn't care. If you divide 1 by the square root of 2, it will give you the same answer as if you divide the square root of 2 by 2. So, and it's the same number of strokes essentially, because you have to do a square root, you have to do a divide, and you have to do a 2, basically. Now, actually, it's one more because you have to do 2 twice one way. But essentially, the calculator will give you the same answer. So if you want an answer to the thing, it doesn't really matter to rationalize it anymore. Okay. On the other hand, it's still a good practice.
Okay, so like, you won't take off points in tests if we leave it like that form, but it's you expect us to try and do it.
Maybe.
Okay.
What you do is you look at when you're doing the problem, you come down, you have 1 over the square root of 2. Now, if that's your answer, and I haven't asked you any question except what's the answer, that would be perfectly fine. But if you're going to use it in something else, okay, it might turn out that you need to be able to do that. And so the whole game here is, if I know you know how to do that, then you don't have to.
Okay.
But if I know you have no clue of what the thing is, then you have to.
Okay.
So if we had a test, for example, and you come down to an answer and you think, can I leave it this way? What you do is raise your hand if we're in class and ask me, okay? Rather than just wonder or sit there or think, should I do it or not, or should I take the extra time to work this out? Ask me, do I need to do it? If it's a question on a test. Now, generally speaking, if I have 8 over 4 and you leave it as 8 over 4, I might not count it off, but I think you're pretty stupid. No, I won't ever say that. But why, if you have 8 over 4, why not write 2? You know, if my wife says, are you coming home this afternoon? I say, yeah, I'm coming home in 8 over 4 hours. That's a way to get divorced. Okay? Why not give her the simple answer? I'm coming home in 4 hours instead of 8/4, which is 2, which I even made an arithmetic mistake, you see? Because when you use more complicated things to say, you might not even get it right. Some people try to impress people by how smart they are by telling them stuff. All right? Generally speaking, if you tell all you know, that's the art of being a bore. And you might be wrong. Okay. So now, again, I answer everything in 5,000 words instead of 20 words like the question, but I hope that in so doing, those of you who have other similar questions have got the answer too. So, but there's no definite answer as to always do it. You should do it when you think it's necessary or when you need to or when you want to make it look better. Okay. Okay, so now was trying to make my way while we were talking there back to the trigonometric appendix D. And so you can see me doing this, of course. What I wanted to look at is some of the things called identities. And then I want to get, for the last 20 some minutes, I want to talk about the notes that are more difficult. But we need to be reviewing trig, and some of you are doing a little more trig review, but I just worry about it a little bit. So when I see some of these things, an identity is kind of a geometric sort of structure where you go from one side to the other. You try to show by some kind of reasoning that the left-hand side and the right-hand side are the same. Now, when I see something like this, I would probably maybe modify the right-hand side and not the left-hand side. So I try to make the right-hand side become the left-hand side rather than the left-hand side become the right-hand side. So these ideas are to decide which one starts out, and then you keep doing stuff until you get the other one. That's what doing an identity means. And a lot of times we have 3 lines here instead of 1 line, because this is supposed to be true for every value of x and y, not just for some. Like I'm no longer solving x squared equals 4 here. X squared equals 4, there are exactly 2 numbers. In this case, this is supposed to be true for all numbers. Okay, so how would I deal with this? I would write the numerator as sine x cosine y plus cosine x sine y, and then divide by cosine x and sine y, after which I will have 2 fractions added together, which when I simplify them will look like this. In other words, when I personally look at this thing, I can see how to do it because I know that formula in the numerator. Okay? What would I do in this problem? Well, in this problem, I look at it a little bit. I see a subtraction in the denominator. I don't see any subtractions or denominators at all over on the right-hand side. However, there are denominators over here in a sense. If I want to change cosecant to 1 over sine, I can make a denominator thing. If I want to change cotangent, I can write that as cosine over sine. So one of the things I notice is I can write this as 1 over sine plus cosine over sine. I have a common denominator. Now I'm just playing with this. I'm trying to figure out what to do. Okay, the trick here is to multiply, like rationalizing the denominator we talked about a few minutes ago. Multiply numerator and denominator by 1 plus the square root of 2. If I multiply the numerator by 1 plus the square root of 2, then I'll end up with sine times 1 plus square root of 2. Okay. If I multiply the denominator by 1 plus the square root of 2, I will get 1 minus something times 1 plus something. That's called the difference of 2 squares. If I have a plus b times a minus b, that's a squared minus b squared. In this case, the a is 1. When I multiply 1 minus the cosine times 1 plus the cosine, I get 1 minus the cosine squared of, in this case, phi or phi, depending on what sorority or fraternity you're in, okay, or wanting to be in, or not wanting to be in. Anyway, so 1 minus cosine squared, that's sine squared. So what this left-hand side becomes is sine times 1 plus cosine divided by sine squared. Sine over sine squared is sine in denominator, so the left-hand side becomes 1 plus cosine over sine. I now divide the common denominator into 2 parts, and I get 1 over sine plus cosine over sine, which turns out to be this. Now, I'm trying to do that in words, not writing it out. We could write it out. You guys probably need to write it out at first, but I'm hoping you'll work toward the time when you can do what I just did without writing it out, using your brain and your mind to say it and try and remember how you said it and so on. Okay? Now, what would I do with the next one up above? Well, because this is complicated and above, I'd work with the right one first. Now, think about it a little bit. What's the difference between sine of x plus y and sine of x minus y? They're alike, but one of them has a plus and the other one has a minus. If I add the two of them together, this plus minus part is going to drop out. So what am I going to end up with? I have to think about that a little bit, but what I'm going to end up with is, if I write this out, oh, no, wait a minute. This isn't plus, this is times. Oh, times, multiply. Okay, well, what I'm going to do is learn a formula. What was a formula for the product? It was the last one, page or so back. I'm going to go back a page or so and see if the thing hides, comes out for me. It is right here. If I have sine times sine or sine times cosine, I can write it as a sum. So use that, one of these formulas, with this one. Because I have, I'm sorry about the gleam. See if I can get it maybe a little bit better there. The white page and the light makes a thing. Anyway, point is, I'm going to use my product formula on that one. You guys ought to do all of these. This will help you bring back the trig things that you're supposed to know more back to the front of your brain or wherever that is, and you'll be able to do it better. Okay, so enough of that, and unless you have some questions about it, we can entertain trig questions anytime. I'd rather do it, entertain the trig questions now rather than when we are writing down what you should have written on your test before you flunked it, which I hope nobody will. Okay, earlier today, we were, or I was, going through with a student about what a symmetric neighborhood is. Now, some of the stuff before this we want to talk about some more, but I want to talk about this a little bit today. These are things, if you can think of all of these things as being in the real line, meaning intervals and things on the real line, or you can think of these things as being in the plane, or you can think of these things as being in 3 dimensions. For example, an interval is what we use in a real line. That's like from 1 to 5. We might be talking about a circle in the plane, and we might be talking about a sphere in 3 dimensions. Okay? A symmetric neighborhood in a real numbers is a bunch of numbers that are at equal distance from a center point, extending out to something which I wrote in the notes here, delta. We're going to use some Latin letters sometimes, or I'm sorry, some Greek letters sometimes to talk about numbers. And this is the Greek letter delta. It's the 4th letter in the Greek alphabet: alpha, beta, gamma, and delta. I will be writing them out for you and spelling them out and naming them for you. You'll get used to them. In calculus, we use a delta a lot, and we use an epsilon a lot, the 5th letter of the Greek alphabet. Okay, but we also use alpha and beta and gamma, and so forth, and theta, and mu and nu and so forth. Anyway, there's 24 of them in Greece, 24 letters that we use, some more than others. All right, this is talking about a set of points. And so it's a little bit complicated. The N stands for neighborhood, the X stands for the center, and the delta stands for what we call the radius. So you can think of, you probably haven't thought of a line segment as having a radius, but it could. If I talk about everything within a certain distance of both sides of something, like if I go from 1 to 3, the numbers from 1 to 3 are, if I take the number 2 as the center, I could describe that as everything, a neighborhood around 2 of radius 1. That would be the interval from 1 to 3. Okay? Now, that's pretty easy compared to some of the rest of this, as you're going to see. So if I just take a set, any subset of the real numbers. Now, what are some subsets of the real numbers? The positive real numbers are a subset. The whole real numbers, all the real numbers are a subset. Okay? The interval from 0 to 1 is a subset. Now, when I say that, do I include 0 and 1 when I say the interval? If I just tell you the interval 0, 1, do you think the 0 and 1 are part of it or not part of it? Well, they could be either. Okay? So to make it clearer, if I say the open interval, O-P-E-N, the open interval 0, 1, that means everything between and not including 0 and 1. If I say the closed interval 0, 1, that means everything between and including 0 and 1. So to be more clear to people, we say closed interval and open interval to tell people whether or not the so-called end points of the interval are part of it or not. And then we can have half closed and half open. We can have half closed on the left, and so I mean we can have include 0, don't include 1, include 1, don't include 0. And we can call either one of those half closed or half open. Okay? So that's just some naming conventions so that you know what we're talking about. All right, well, let's take a set. And by the way, we could have a set of rational numbers, all the fractions. Okay? That could be the set. Take a subset, take a set D. Take a point in the real numbers. Now, what we want to do is compare the point to the set. So, first of all, is the point a member of the set or not? We had membership the last couple of days. If you're in the set, you're called a member. If you're not in the set, you're called not a member. Okay? So, but that's not what we're talking about. We're talking about, are you an interior point? What's an interior point of a set? Well, X naught is an interior point if there is some symmetric neighborhood around X naught that is totally inside the subset. Now, this means the set has got to be solid, so to speak, number-wise. Okay? An interior point, everything around it is also in the set. Okay? An exterior point is an interior point of the complement of the set. Now, if we take I don't know, a house, everybody knows if you're inside the house or outside the house. If you're inside the house, then there ought to be space around you, totally surrounding you, that is also inside the house. If you're outside of the house, there ought to be a space around you that's totally outside the house. Okay? What if you are stuck in the wall so that part of you is inside and part of you is outside? It's called a boundary. Okay? So we have interior points, exterior points, and then we have boundary points. A set is said to be open if every element of the set is interior. Now think about the interval from 0 to 1 called the open interval, but think about 0 and 1, not including 0 and 1. Like a half is an interior point. Why is a half an interior point? Because I can surround a half with a neighborhood that's totally inside 0, 1. What about 1/10? Is that an interior point? Can I surround the number 1/10 with some numbers that stay inside 0, 1? It's a smaller little neighborhood, but it is still true.
Yeah.
Every number between 0 and 1 is an interior point of 0 and 1, of the interval 0, 1. Okay?
So,
Now, and we'll be doing this a lot. Sorry, go ahead.
so just making sure I got this right. So basically, how you set this up would be you have a parentheses, 0, then a comma, then a 1, then a parentheses. And then anything in between those would be an interior point.
Yes, in this case.
Okay, just making sure.
Okay. Now, what's a boundary point? A point is a boundary point of the set if every neighborhood, here's a universal quantifier, every neighborhood contains a point in the set and out of the set. See, an interior point says some neighborhood only is in the set around the point. An exterior point is some neighborhood exists that's only outside. A boundary point says every neighborhood has something inside and something outside. Okay? Now, the hardest one, an accumulation point. A point of a set is an accumulation point if every symmetric neighborhood contains at least one point of the set different from the center point. Every neighborhood contains a point different from the center point. So what you should think about is if I have a point and it's an accumulation point, the word accumulate means to build up. The other word we use is cluster point. The idea is if I have something that's called a cluster point, then there's suppose that we go to school and we have class and you guys cluster around me. Then we are disobeying the spacing rules. Right? Now, if you take the President of the United States, for example, and I'm not talking about politics and I'm not talking about who's president. You take the President of the United States, we have an organization called the Secret Service. And the Secret Service makes the president a cluster point. In other words, the president is always surrounded by Secret Service agents, unfortunately, in terms of having to be that way. But what does that mean? That means there's somebody as near to the president as necessary to take care of the problem that might be around. That's what a Secret Service agent is like, okay? And I don't know if you have ever met anybody know any Secret Service agents?
My former engineer professor husband was.
Right, okay. Well, it's a special kind of person, honestly. I worked with police for 30 years. I work with the Secret Service, and they are an interesting group of individuals in terms of just everything about them. So if you know somebody like that, you might find they're an interesting person to talk with sometime. Not because of what they did, but just because of the way they sort of view the life, United States, whatever. Anyway, so an accumulation point means there's lots of stuff around. So for example, take the open interval 0, 1, not including 0 and not including 1, okay? 1/2 is an interior point. 3/2 is an exterior point. 1 is a boundary point. because you put any neighborhood around 1, it will include a piece of the interval, and it will include stuff not in the interval. And 1 is a accumulation point because it includes points that are in the interval. What are the accumulation points of the open interval from 0 to 1? The answer is the closed interval from 0 to 1. Number 0 is a boundary point, but it's also an accumulation point. Number 1 is a boundary point, but it's also an accumulation point. And so all the accumulation points are the interior points and the boundary points. Okay? Now, let's suppose we take the set 1, 1/2, 1/3, 1/4, 1/5, and so on. It keeps going. What are the interior points of that set? What of those points has neighborhoods around that are also those points? And the answer is, you have to think about this. We're running out of time. There is no interior. The interior of that set, 1, 1/2, 1/3, 1/4, there's a bunch of points. There is no interior. It's the empty set. What are the accumulation points? The answer is 0 is the only accumulation point. Now, if I have a set and a point in the set is not an accumulation point, it's called an isolated point. An isolated point means you put a neighborhood around it that doesn't contain anybody else in the set. When we are in class, all of us are supposed to be isolated because of the virus. There shouldn't be anybody sitting with anybody else close enough, all right, to be considered an accumulation point. Now, the analogy doesn't go very far because we have just a finite number of points. When you have a finite number of points, they are always all isolated. Okay? Anyway, these are some of the things we're going to be using because what calculus is about is talking about what happens to something near to something else. So we have to understand how to talk about something being near to something else. And these are some of the critical things we'll be talking about to explain to somebody what is near. Okay. McKinley, you asked about what will be on the first test. Don't worry about it yet. Okay. In other words, just keep studying the stuff we're doing. I'll be explaining precise. Nobody else besides me knows what's on the first test. So asking the other students doesn't do much as far as answering. But
not to interrupt you, I think like sorry and all, but I know this is a thing that college classes do, but like, is there a study guide or not? Is that not? Because I know some college classes do it, but most don't. So do you do anything like that, or just use the notes?
Right now, I'm using the notes. Once you've got kind of the notes going on, we can then sort of summarize them and do other things. Okay.
Okay.
By the time we get to a test, you'll know exactly what's going to be on the test, not in terms of what the problems are, but I will try to clarify because nobody knows right now how hard I am or how bad I am or how unreasonable I am on tests and stuff. And so for the first test, I'll try to be as careful to help you know how to study for it as I can. At the moment, though, don't worry about it. Just study everything. All right. Now, the test will never be over everything. I'll cut it down. But some of the things we don't ask about, I still want you to know about. So, does that help you?
Yes.
Basically, just study hard. If you guys study enough, you won't have to worry about the test. The test will be easy. I'm not worrying about the test. I'm worrying about your knowledge. Okay. What I'd like to do, by the way, is give you all A's today. Get that out of the way. So we can then worry about learning something. If you like, we don't have to have any tests. Don't have to have any homework. Oh, I just learned something.
Do that.
Okay, well, let me do something here important for what we're talking about right now.